The fundamental theorem of calculus is the well-known keystone of calculus, but it can appear a bit arcane at times. Today, I want to develop some reasoning and intuition for why this theorem works. This will not be a rigorous proof, but rather a simple explanation of the theorem. With that in mind, let's get started. Consider a general function f of t. It could be any function, like this one, or this one, but we will consider this one as an example. Suppose we want to find the area under this function from t equals a to t equals b. How would we do this? One idea is that we define a new function, g of x, such that g of x represents the area under f of t from t equals a to some t equals x. We can write the definition of g of x as the following integral of f of t, which simply expresses the same idea in mathematical notation. Notice how the value of g of x changes as we vary x. We would like to evaluate g of x at x equals b to find the area in question. To do so, we will need to learn a little bit more about this function, g of x. Let's examine the rate of change, or the derivative, of g of x at some x value. This derivative is dg divided by dx, which means that it is the ratio between a small change in x, dx, which causes a small change in g, dg. We will hope to compute this ratio. We can depict this derivative visually by considering a small change dx and noting that this additional dark blue area represents the change in area, dg. Let's zoom in on this part of our diagram to get a better understanding of what's going on. To find dg dx, note that we can approximate dg with the following rectangle, which has a width of dx and a height of f of x, as this point up here has coordinates of x, f of x. Now, it is important to stress upon the fact that at this moment, this is just an approximation, as the rectangle in this case is a little bit larger than the actual value of dg by this pink area here. However, as we change dx from being a small but finite quantity to an infinitesimal one, this pink area shrinks in size towards 0, and thus, in the limit that dx tends to 0, we can see that dg can be said to be precisely equal to the area of the rectangle. Thus, we can write that dg is equal to f of x times dx, as the latter is the area of the yellow rectangle. This little equation up here is actually almost all we need to construct both parts of the fundamental theorem of calculus. Notice how we can take this statement and substitute it back into the expression for the derivative of g of x and get the following. Now, we can effectively just cancel the dx's to get that the derivative of g of x is simply f of x. Finally, if we just note that g of x was originally meant to represent the area under f of x from some t equals a to t equals x, we can substitute in the definition of g of x into this equation to get this. That complicated looking equation down there is actually none other than the first part of the fundamental theorem of calculus. And all it is saying is that if one constructs a function that finds the area under another function f of t, then the rate of change of such a function at any t equals x is just f of x. We can also quickly derive part 2 of the fundamental theorem using what we have here. Putting part 1 to the side for the moment, let's return to the original question of areas and how we want to find g of b. Notice how this relation for the derivative of g of x implies that g of x is of the form capital F of x plus c, where capital F of x is a function such that capital F prime of x is just little f of x and c is a constant. You can confirm for yourself that this equation for g of x is valid by taking the derivative of both sides of that equation, and after noting that the derivative of a constant is 0, you should arrive upon this original constraint equation for g of x. With that being established, all we need to do to find g of b is to find the specific value of c such that g of x is precisely the area function that we are looking for. To find c, we can realize that g of a should be 0, as g of a represents a region of 0 width, and thus 0 area. Further, if we plug in x equals a into our equation for g of x, we find that g of a is equal to capital F of a plus c. We can then equate these two equations to solve for c and find that c is equal to negative capital F of a. Therefore, we can say that g of x is equal to capital F of x minus capital F of a. It follows that g of b is equal to capital F of b minus capital F of a. All that's left to do now is to simply note that g of b was defined using this integral expression that gives the area under the curve of f of t from t equals a to t equals b. So we can substitute that in to find that this definite integral is equal to capital F of a minus capital F of b. That is the second part of the Fundamental Theorem of Calculus, which states that if we have a function capital F of x such that capital F of x is the antiderivative of another function little f of x, then the area under little f of x between two bounds can be found by subtracting the value of capital F of x at x equals b from that at x equals a. With that, we have found derivations for both parts of the Fundamental Theorem of Calculus. Hopefully that proof gave you some intuition and background for why the Fundamental Theorem works. If you enjoyed this video, please consider supporting the channel by subscribing. Nonetheless, I hope you have a good day, and I'll see you all next time.